Welcome back. So now we are going to talk about one of the very important pattern in the system design, and this one is extremely common in the real world system. Even though many people don't explicitly recognize it, but we'll call this topic handling conflict in the distributed system. So in the system design language, this is often referred as a contention. Okay, so might be this word is coming, so it's the same contention. So what is this? So let me start with a very simple situation so that we can build the intuition properly. So imagine there is one seat left in a movie theater, and now there are two user A and user B. Okay, so user A and user B are there, and they are trying to book that same seat almost exact at the same time. Okay, so from the business perspective, what is expected? The rule is very clear. Only one booking should be succeeded. But inside the distributed system, we are having one seat here and two users are contending for this particular seat. So in distributed system, these things are not as simple as we are thinking. Both requests may arrive nearly at the same time, or possibly even handled by the different server. Okay, so now think carefully in this. What happens inside the system? User A requests check the database. Okay, this user A request is check the database, okay, whether this seat is available or not, and almost at the same moment user B also request and check the seat availability. Both will get, yeah, seat is available, right? Suppose it is coming at 10 a.m. At the same moment someone is also trying to do the same operation. So both are getting, yeah, seat available. Here is also seat available, right? So both request checks and database, and they got the confirmation, yes, seat is available. Now both proceed to book the seat, and suddenly we have sold the same seat twice because we already checked it, right? And it's coming, it's available. So both is going to make the payment and book the seat. So one seat booked twice, for user A also and for user B also, right? So let's visualize this timeline. So because this is where problem becomes very clear. Okay, so let me write in a different way. So user A is there. Okay, user is going to read the seat availability. Okay, and if it is true, then it's going to write a make a payment. Okay, user B is coming, it also going to do the same operation at the same moment. It also getting seat availability, and it also going to write. Okay, so what is happening? The final result, double booking. So this is a bad experience, right? So what we are seeing here is not just a bug, it's a fundamental problem called race condition. In thread language, we call it, you might have heard this word, terminology, race condition. Means for one thing, there are multiple chasers, where multiple operations are happening on the same piece of data at the same time. Okay, but they are not aware of each other. Okay, both operations are trying to do the same operation, but both operations are not aware of each other. Okay, so the key issue is that the read operation and write operation are separate. Okay, now coming to the solution path. So problem is coming because read is happening in some different thread and write is happening in some different thread. Okay, so this is the problem. So between reading the data and writing it back, so whenever reading the data, when you are writing the data, in between another operation can come, right? And they just interleave this operation, or they can sneak in the operation and change the state. So the root cause of contention is very important to understand. It's not just multiple user, it's just user is trying to modify the same shared resource at the same time and without any coordination. Okay, so in this situation, this situation is not very much rare. It happens in booking system, banking system, or anything where multiple users are trying to take some shared resource. Okay, maybe inventory system, social media counters, okay, many more places. So not the first instinct to solve this problem is usually very straightforward. Okay, because we know that if somehow I make this operation as a one unit, my problem could be solved. Okay, so let's see, we try to make sure that only one user can access the resource at any point of time, and that leads us to concept of locking. Okay, so locking. So in a very high level, locking is nothing but it says whenever any user is coming for booking the seat, it should lock that particular seat resource so that no one can enter at the same moment unless until the current user is releasing the lock. Okay, so if one seat is there, so it's saying let's lock it, and this locked by some user, some thread. So whosoever coming first is going to take a lock on this resource. Now it will read the seat, it's available, it is going to book the seat. Okay, and once booked is done, then you can release. So in between, if other threads are coming some different operation or same operation, they have to wait. Okay, they have to wait because this thread is now no more shared, it is locked by one user. Okay, so let's say before updating the seat, we acquire a lock on the seat. Once the user acquires the lock, no one else can modify the resource until the lock is released. So this is how this workflow happens, right? Now, because user A acquired the lock first, user B is forced to wait, right? And only after user A complete the booking and release the lock, then only user B can proceed. And this ensures that there is only one update happens at any point of time, and so correctness is maintained here. So since they are all waiting here, so this data cannot be corrupted because only one user is going to inside that and it's doing all the operation normally. Okay, but this thread is waiting. Suppose more threads are coming, they're also start waiting, right? Because this is logged. So now so B will proceed until this get released. So this ensures that data is correct, okay, and correctness is maintained. We have solved this double booking problem, right? This is resolved now. At any point in time, only single booking will happen. But now we need to slow down and think like a system engineers. We are not going to solve only one problem. Your solution should not create a new problem. Okay. Here, what is happening? What happens when thousands or millions of users trying to access the same resource? This is a seat booking, right? Resource. There are multiple threads are trying to book that resource. So what will happen? They all have to wait. So this waiting process is going to make your system slow. All of them will be waiting for the lock, and the system going to become slow. Throughput drops significantly because we have effectively serialized the access to that resource. Because earlier it's a thread-based parallel system was going on to book the system. Now we have serialized this operation. First, serialize means there are two operations, read and write. So all these are now going in one direction. In one thread enter, it will do the both operation, exit, then another thread will enter, okay, A and B, then B will come, it will also do the same operation, then exit. So though we are having concurrent user, multiple user, but inside this operation, we are doing single thread by thread operations. Is going to slow down, right? Slow down means again going to down the throughput significantly, right? Okay, so there are more deeper problems as well. In distributed system, locks are not as simple as they look. if the system crashes, suppose I have taken the lock and system got crashed while holding the lock, that lock never be released. Remember that. If multiple resources are locked into different orders, we can get into a deadlock where two processes are waiting for each other, forever. And this implementation distributed lock require coordination service, network communication, and handling the partial failure, right? So these are the major, problem or deeper problem that is coming when you are going to implement this methodology. Okay, so here we have learned very important trade-off. Locking gives the correctness, but it does not scale, especially in high concurrent system. So now we are trying a different mindset now, and so instead of preventing the conflict completely, what if we allow the multiple user to attempt the update but detect conflict when they happens? Okay, so this is called optimistic concurrency control. What is this? We call it OCC, right? So in this approach, when user reads the data, we also attach a version number to that data. It's saying when one operation is there, suppose read, and I'm just writing in that way. So whenever any thread is coming, at that time, it start going to read the is going to read the seat availability. At that time, I will append one version. Okay. So when user reads data, we are going to attach a version number to that data. So when user is try to update it or try to book it, we check whether the version has changed or not. Because while reading, suppose I was having the version 1, and while updating or writing, here if it is version 2, it means someone has come here and modified the version. Version will get modified whenever someone else is going to read the data, right? On each and every read, I am going to increment this version. So we are going to check whether this version has changed or not. If this has not changed, then update is allowed because no one has changed that. But if it has changed, it means someone else has already updated it. So we reject the operation and ask for user to retry. Okay. So hope this is clear to you. So let me draw one flow diagram. So user A is there. Okay. Is going to read. Once it is reading the seed data, I am going to add some version 1, and then update and write. When write happen, then I am going to update the version again. Now it become version 2. Suppose at the same moment when this was happening, user B came, it also read the data. Okay, it also got the version 1, suppose, is going to update. Now this version 1 is not going to match this version, which are the latest one. Okay, so this will fail and again move to retry. Okay, hope this is clear, right? So here both user read version 1, user A update first and change the version to 2. When user B trying to update, the system detect that version that changed the version that user B is asking, it's already changed. So it is going to reject the update. So only one operation succeed and correctness is preserved without using the logs. Again we are able to achieve here correctness, but without log. Okay, so here till here we are on the same page, right? But this approach also has a major, it also has a major advantage, that is there is no waiting here. We are talking about so like system will become slow because multiple threads are waiting, and then it will lead to race condition. So this is not going to happen. Okay, so this is not going to happen. So no lock is held, multiple user can operate concurrently, and this makes the system much more scalable and performant compared to the locking, the previous approach. Okay, let's think a bit deeper. What happens when contention is very high? Means there are suppose one celebrity show is about to happen and lakhs of people are trying to book that seat. So concurrency is very high, contention is very high. Then what? So like one more example you can take, like when flash sales happen on the e-commerce website like Amazon or Flipkart. So there are limited number of iPhones are there and people are trying to book that. In that case, most of the updates will fail due to version mismatch. Okay, because this operation is having what we're doing it here. Again, one user B, then user C will come. They are going to mismatch this because this one has purchased this, the version is updated, right? So now this is going to fail due to version mismatch, and user will keep retrying, and this leads to wasted work and increase the load on the system. So now we understand an important principle here. Optimistic concurrency works very well when conflicts are rare or very less. Okay, so optimistic concurrency lock, it works very well when you have conflicts rare. Rare means very low. Okay, in that case that is okay, but the example that I have taken of flash sale, this is going to cause one issue, right? We saw that. So at this point we have to explore, we have explored two fundamental approaches. Okay, till now what are approaches? Locking, which prevents conflict but reduce the scalability, and optimistic concurrency lock, which allow conflicts but handle them efficiently when they are rare. Okay, but the real question is what happens when contention is extremely high or very high, when thousands of users are attempting to the same resource at the same time. Neither locking nor OCC alone is sufficient, both are going to be failed. And that's where we move to the next level of design, where instead of fighting contention directly, we are start restructuring the system itself. Okay, we are not going to fight or counter the conflict directly. We are going to restructure our system in such a way that is going to handle those conflict at a scale. Okay, so let's see in the next lecture with the new concept. Okay, until then, bye.